Okay, so let's start our lecture today. Okay. Okay, so let's continue the proof of this Corollary 2.4.7. Okay. So okay, so yes, this is like x theta, and then this is x, and then this is space gamma, and then this is okay. Okay, so this is okay, so this is a space x hat. Okay, so which is the space x to the quotient out by the group action by this gamma. Okay. Okay, so now okay, I think okay, so we want to use 0 to 4 yeah, we want to use the theorem 10.4.2, which given a subgroup of the group of subhomomorphism. So we want to construct such covering space. Okay. Yeah, we want to use the part B of the theorem 10.4.6. So this way is actually connected with this okay. So okay. Oh, okay. Yeah. So I think I am left to show that this x is yeah. I think yeah. So I was left to show that this x is locally simply connected, right? So okay. So it is locally simply connected because yeah. So I think last time I picked like a locally even cover set, right? So then it's you had and then it's a P upstairs. Okay. It's a P. Yeah, it's you can yeah, I'm fine. Yeah, sure. Yeah, I'm good. Thanks. Oh, okay. So okay, so the only thing I need is that I need to construct a homomorphic upstairs, right? So yeah, so that is yeah, so okay, so to pick any element, okay. So let's say this loop R is at this is at P in this pi 1 of sorry, it's a little bit jagged. So So then because yeah, let's do beta p. Okay. So and also since okay. Yeah, I think okay, so okay. Okay, so since this gamma is so this is a local convergent, right? It's a homomorphic. So therefore, we have the property that yeah. So this implies the image actually has U, right? So this implies that okay. So this is a loop and the image has U. So therefore, yeah. So this lies in this I1 of U beta. Okay, so now, because this U is independent, so there's a homomorphic effect. And then by the I think by the yeah, by the homotopy lifting property, then there's a homotopy outspills. Yeah, and then everything is preserved, right? Yes. Okay. 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 Go ahead. Okay. Okay. Yeah. Because yeah, you specify a point upstairs, and then there's a homotopy downstairs. So the homotopy lifting property says there is a unique lifting of this homotopy with the same base point. Okay. Yes. Is that with the same base point in the tree? Yeah, because it's by the unique lifting property, right? So for each path there is a unique lift. Yes. Okay. Yeah. That's true. Okay, so therefore that homotopy must be if you do the projection, then that must be this projection must be yeah, it's a lifting. Okay, so therefore you project it down. So therefore it gets the original map. Okay. So therefore, okay. So therefore the okay. Okay. So therefore the lifting of this constant loop. The lifting of this constant loop must be the constant loop, right? Yes. Yes, it must be constant loop. Yes, exactly. Yeah. So yeah, I think this shows the result that is the concept. So okay. Lifting of constant. Yeah, that. So otherwise, it will be. Wait. It's a continuous map, right? Yeah, it's a continuous map. Yes, it's a continuous map. Yes, it's a continuous map. Yes, and then yeah, otherwise it will be it will be disconnected. Okay. Otherwise it will be disconnected. Okay. 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 So now let's see. Okay. So now we have it. Okay. So now we have it. Okay. So we have that this exterior is a locally semi-connected. Yeah. So it's a semi-connected. Sorry. Locally semi-connected. Okay. Okay. So then it's locally compact. Okay. Locally compact. Why is it locally compact? Okay, so because this X is locally compact, right? So X is locally compact. So therefore, okay. Okay, so I think the same argument also works for the compactness. Okay. Yeah. So you can always pick a even a color set and then take its pre-image. Then you can do like a restriction on another like intersection of the open intersection of the open set, and then you do the inverse. Yeah, and then that will get you you can apply the same argument here. Okay, that's the idea, and then you show that it's you show that there's a compact set. Yeah. Yeah. Should be relatively compact. Right. So relatively compact. To take the closure. Oh, okay. Because the closure is okay. Okay. Closure in place. Okay. Okay. All right. So. Okay, so now let's see. Okay, we have this as locally compact. Okay, we have a locally compact. Yeah, locally compact. And then what's next? Okay, so we have a pre-compact set. Yeah, so I think I think you can do like a subspace closure, like you can argue that this inverse this I think you can do argument of this v the image of this v under the image of this v under this gamma inverse closure is exactly the same thing as the image of under this map of v closure. Okay. And then we know that the image of compact set is under we know that this image is this image of V, which is the same thing as the pre-image of this gamma. Which is the same thing as the pre-image of this gamma is also is compact. Okay. So therefore, we show that it's compact relatively to the subspace topology. And then that implies that it's compact in the regular topology. Okay, so so that shows it is relatively compact. Okay. And then so this shows that this X is actually locally compact Hausdorff. This X tilde is locally compact. Locally compact, and then locally compact. Yes, and then what you do is that you so you apply this lemma. Okay, so then you apply this lemma. Okay, you apply this lemma 10.4.6, and then what you get is that so since this gamma is a subgroup of the group of subgroup. Okay, we want to show that this. I think so, right? Because because this gamma. So remember, this gamma is a subgroup of the group induced. What is the gamma? Okay, so this gamma is a subgroup of part 1, right? And then when we are talking about the so when we are talking about the group action by this gamma, we are really referring to the one-to-one correspondence between the we are talking about the one-to-one correspondence between pi 1 and the Dirac transformation group. Yes. So then because the Dirac transformation is actually a self-homomorphism, right? So so y in x, so y in x properly discontinuously. Yes, we show that it's free. Okay, we show that it's free. Okay, by the last part of the theorem. The first theorem we prove. But the last part of the first theorem we prove, we show that it's free. And then y is probably discontinuous. I think there's a lemma showing, there's a theorem showing that, right? Okay, theorem 10.4.5. Okay, so this is a lemma showing that the group of the Dirac transformation group actually acts properly discontinuously and freely on this X tilde. Okay. So Okay. Okay. So wait. So this subgroup. Okay. 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 So therefore, okay. Yeah. Oh by 5. Oh, 1 by 5. Okay. Okay. Yeah. So. Yeah, so therefore we have the result, right? So therefore we have the result. Okay. So therefore we have the result that the yeah. So the quotient group is actually yeah. Sorry, the quotient space is actually a covering space. Okay, it's a covering space. And also since this ambient space is connected, right? Yeah, so this X tilde is a connected space. So therefore we get that this is the connected covering space. Wait. Shoot. Yeah, so this space is connected. Okay, so this is a connected covering. Wait, why is it covering space? Okay, so by the things that we just proved, right? So this we proved that this is a covering map, remember? And we also show that this is connected because this is connected and this is a continuous map. So therefore this is a connected covering space. Okay. So let's see. So why there's a unique? So why there's a unique? Okay, so unique up to equivalence class. Okay. Because we know that this X is unique, right? Up to equivalence class. Okay. Yeah. Okay. And then this space. Okay, because this group is actually a fixed sub. Yeah. So this is a fixed subgroup, right? So this is a fixed subgroup. Wait, no, sorry. So let's gamma be a subgroup. There's a unique connected space here that for some. Okay. Okay, so we want to show that. Sorry. Okay, so let's drop the uniqueness for a while. So we're still not done yet because this. Let me see. Okay. So this theorem 10.4.6 guarantees the existence of such connected covering space with the covering map gamma hat. Okay. So now what we want is that we still want to show that this gamma this gamma hat push forward of this pi 1 of. Okay. So we want to still that to verify. Okay. So want to verify that this gamma push forward from this pi 1 see this is x not hat. Okay. So this is pi 1 of x hat, x naught hat to the pi 1 of x naught. Okay. Maps pi 1 x hat of x naught hat isomorphically onto gamma. Okay. 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 So y onto gamma. Okay, I think we just showed that, right? We showed that, okay, so, okay. Yeah, so what we showed is that, okay, so, yeah, so this is a base point in x tilde. And then this x naught is the same thing as the projection, Korean projection. And then this is another parallel Korean projection by this, let's say that this is the quotient map. Okay. So which is I'll just write, yeah, this is the quotient map. The equivalence class, sorry, equivalence class, yeah. The quotient map, yeah, the quotient map, and then the equivalence class, and then, and then, okay, so we know that, okay, so this is what the theorem proved, okay, so we know that, so, okay, so we know that so this chi from wait no oh okay. I think I should have used a different letter here. Yeah. Okay, so so what is about student? Okay. so okay, so I think what we show is that okay, so I'll use the notation for the notation we used before. So basically, this gamma now denotes actually I think these are the same. Okay. So this gamma is actually a subgroup of the group of self-oriented a subgroup of the group of self-homomorphism of this covered space X student. The X property is confusing and fitting on this X student. Okay. So I think that's the same thing as so that's the same thing as the gamma that we are defining here, which is the covering space subgroup of the Danish transformation group. And then we also have this gamma hat as a subgroup of this gamma. Okay, so this is subgroup. Okay, so now we know that this chi from this gamma. Wait. Oh, okay, I see. Okay. Oh, right. Okay, I think we showed in the first part actually. We actually showed in the first part that this gamma is actually the the quotient space X is connected locally simple and locally compact also. This gamma from X to X in local quotient space and then okay. Okay. Subgroup of the group of subgroup X tilde the X property is continuously and freely on X tilde. Okay, so yeah, let's stop here today. Oh, sorry, late. Okay, so yeah, I will continue from here next time. Okay. Thanks for watching.